All right, it's lecture 6, and as you know, today's Monday the 12th. We have our mini exam today. So I'm hoping to just spend 25 to 30 minutes on a few more examples and reviewing the second fundamental theory of calculus, which should help you for the mini exam. And then we're going to plan to take it starting in here at this class at about 11:40. We'll have about 40 minutes to do the mini exam as well. All right, let's start with more trig integrals. And I realized that one of the examples I did at the very end of class the other day, actually I think I did cos squared. That's okay, we can do sine squared. Actually can be done with integration by parts, and actually it's in the book. I tried it by using integration by parts twice, and it really wasn't helpful that way, but what I should have done instead is use integration by parts once and then use a trig identity. Let me show you the way that I did it before. Last Friday, we did it with cos squared. I used the trig identity and I said cos squared equals 1/2 plus 1/2 cos 2x. Sine squared is almost the same thing, except for the minus sign here. Sine squared actually equals 1/2 minus 1/2 cos 2x. Not sine 2x, but cos 2x. That is correct right there. It's got to be, actually, if cos squared x equals 1/2 plus 1/2 cos 2x. Sine squared and cos squared have to equal 1 when you add them together. So there's the only way it can be is this. And that's easy to integrate. You get 1/2 x minus 1/4 sine 2x plus c. But you also can do this with integration by parts. But just do it once instead of twice. U equals sine x and v prime equals sine x. Sine squared is the product of sine and x with itself. U prime would be cos x. V would be negative cos x. Use the integration by parts formula. U times v will be negative cos x sine x minus the integral of v times u prime. The product of those two things is plus the integral of cos squared. But now, the best thing to do here is replace cos squared with 1 minus sine squared. You'll be able to do the integral of 1 pretty easily. The integral of sine squared, you can swing it to the other side, so you can solve for the integral that you want to know. It's the same integral as that one. I get negative cos x sine x plus x minus the integral of sine squared x. Yeah, now add that integral to both sides. And then divide everything by 2. Because you'll have 2 times the integral on the left side equals this. Divide everything by 2 and then tack on your plus c at the end. The integral of sine squared x is negative 1/2 cos x sine x plus 1/2 x plus c. These are both correct answers. You can see the 1/2 x's definitely match up. Does that function match up with this function? They are the same. If you use a double angle formula, replace that with 2 cos x sine x. 2 and the negative 1/4 cancel to give you negative 1/2. They are the same. That's called a double angle formula. These are the same function. They look different, but they are the same. Either one is okay. I think I mentioned last Friday, I always tell my multivariable calculus students to memorize this one. It's a bit quicker. I think it's worth remembering. Next Friday, you have the gateway exam. It's coming up quick. what's that now? 11 days from now. It's all about integrals. It's not, and again, you get more than one chance to pass, though you have to take a different version. There are 4 different versions, the one we take in class and 3 retakes that are possible. I believe every one of those 4 has an integral of the following form on it. Cosine times to some power times sine to some power, where at least one of these powers is odd. If they're both even, it's not so easy. So we have cosine of x to the 6th power times sine of x to the 5th power. I'm making mine a little harder than comes from the gateway, but it's okay. At least one of these powers needs to be odd. That one is, for this integral to not be too bad to do. If I made them both even, and especially if I made them both 6s, it would be a nasty integral to do. But the fact that one of those powers is odd makes this doable with the trigonometric identity and the substitution. What you want to do is you want to take the one with the odd power, in this case the sine, and break it off. Take one of the factors of sine and break it off. In other words, write it like this. And then, what you're going to end up doing is you're going to end up letting w equal cosine of x, because then dw will be negative sine x dx. It's almost there for you. What do you do with that? You replace it. You replace sine squared with 1 minus cos squared. This is the same as sine squared x squared, which is 1 minus cos squared x squared. And so if you let w equal cos x, you've got a w to the 6th there, and you've got a 1 minus w squared quantity squared right there. And this is going to be negative dw. dw is negative sine x dx. So you get the integral of w to the 6th times 1 minus w squared quantity squared, negative dw. You can bring the negative sign out in front. You can square things first if you like. This is 1 minus 2w squared. Thinking Greek here. 1 minus 2w squared plus w to the 4th. I think I won't bring my negative out in front. I would just multiply by w to the 6th and I'll negate everything. So I'll get a negative w to the 6th plus 2w to the 8th minus w to the 10th dw. I negated everything. Took that negative sign and the w to the 6th and multiplied times that. That's right. Now this is not too hard to do. Negative 1/7 w to the 7th plus 2/9 w to the 9th minus 1/11 w to the 11th plus c. And then it's an indefinite integral. You need to replace w with cos x. So you get negative 1/7 cos to the 7th plus 2/9 cos to the 9th minus 1/11 cos x to the 11th power plus c. There's no guarantee that Mathematica is going to put the answer in this form. If I had to guess, I'd say probably it won't. You know, with all these trig integrals, it's pretty unclear what form it's going to do it in. I can use the integral symbol on the palette over here, but you also can use a built-in function just called integrate. Cos x is being raised to the 6th power times sine x, which is being raised to the 5th power. Integrating with respect to x. Yeah, it looks different. It's hard to imagine that's the same thing. But it actually is. I'm pretty confident I didn't make a mistake. There are power reduction formulas that allow you to write these powers of cosine in terms of cosines of different frequencies. It's pretty amazing. Unless I made a mistake, those should be the same function, or at least a vertical shift of each other. They could be differ by a constant. So you can expect something like this to come up on the gateway exam. By the way, historically, in the gateway exam, the Calc 2 gateway is harder than the Calc 1. It's about a 50% pass rate the first time. Usually about half the class needs to retake it. It doesn't have to be that way for you guys. It can be a higher percent. I'm just telling you that's what's happened in the past. It doesn't have to be that way for you. You can study really hard and have a higher pass rate, maybe 80 or 90% on the first time. Okay? Practice. So we keep practicing. We're going to keep taking quizzes, mid-class quizzes, at least up till the gateway. And then after the gateway, it might be just more once in a while. Mid-class quiz. All right, let's spend a little bit of time then with the second fundamental theorem of calculus. There will be a mini-testing problem related to this. I know it's a difficult concept for people. Let's say you had to differentiate an integral something like this. Looks pretty nasty. How in the world are you going to do that? It's definitely possible, but you have to be careful. The fundamental theorem of calculus itself, the second fundamental theorem of calculus, which, again, not everybody calls it the second fundamental theorem. Sometimes they just say fundamental theorem. It's a different form. I call it the antiderivative construction theorem. Actually, the textbook does too. The statement is like this. To differentiate an integral like this, where your variable that you're differentiating with respect to is this upper limit, which it can be. You certainly can make that upper limit a variable. Make the right-hand limit of your integral change to get different integrals for different x's. That's definitely possible to do. It's like the d dx and the integral sign kind of cancel, leaving you with the function you started with. What letter should I put inside? It is important here. Yeah, put x. Those letters, this one, and this one, they all need to match. Okay? The letter right there, the T that I use, that doesn't have to be a T. Could be a W, could be a U, could be a Z. Doesn't matter, it's the same answer. Physics teachers will often put an X there as well, but that really is sloppy. It is definitely a good idea conceptually to put a different letter there. If the graph of f is above the axis, and A happens to be right there, for any given x, that function that you're differentiating gives you the area under the graph for that x. But as x changes, you get different areas. This thing is a function of x that we can differentiate. We've almost got it here. This is of that form almost, except it's now x to the 11th instead of an x. So we have to use the chain rule because that's the inside function. When you plug a number in for x, you do x to the 11th first before you integrate. For extra clarity, you don't have to do this on the test question, but you can if you want. For extra clarity, you could let capital F of x be the integral from 7 to x, and again, the 7 is irrelevant. I could have put any number down there. It doesn't matter. Let capital F of x be the integral with an x up top, instead of the x to the 11th. Let g of x, say, be x to the 11th. What you're trying to find here is the derivative of the composition, capital F of g of x. That's a situation for the chain rule. You got an inside function, g of x, and an outside function, capital F. The chain rule says take the derivative of the outside, plug in the inside function, and then multiply times the derivative of the inside. Now just apply it in this problem. The derivative of capital F is the little f that you're integrating, the cosine, with x in place of t. That's what this is. You're integrating a little f. The whole integral is the big F. The integral with the x up there is the variable. That's the big F. The derivative by this fact is the little f you integrate with an x in place of t. However, careful, with the chain rule you need to not replace x with x, but instead replace it with g of x. In other words, x to the 11th. So in place of the t goes an x to the 11th. Then the chain rule says multiply times the derivative of the inside function being x to the 11th, to get 11x to the 10th. Now just simplify a little bit. 11x to the 10th, cos, square root, multiply those exponents, x to the 55th power plus 3x to the 22nd power. Yikes. That is the answer. I do believe I did not make a mistake. Is this useful? It actually is. There are many situations where you have functions that can't be integrated, like at least in terms of finding nice formulas for them. I can't imagine trying to find an antiderivative of that. But you can still differentiate these integrals. And that is useful, especially when we get back to probability later on. We're going to use this a lot with the probability. It'll have applications in that subject. But it's got applications all through calculus as well.
Wait, so is that 11x to the 10 times cosine? Is that function the antiderivative of the original?
This function is the derivative of this integral.
It's the okay, so
Derivative of the integral.
I'm
And because it's an x to the 11th there, it's not equal to this. Because you got that x to the 11th there instead of just an x.
okay, so a derivative of the integral is the original function, but you'd have to plug in x to the 11th.
In this case, yes, and use the chain rule. Yep.
Does it need a plus c at the end or no?
No, because we're differentiating.
What if the lower limit wasn't a constant? If it was a function?
If it was a variable, then you have to deal with that in a separate case. Your exam question is not like that. But for example, if it were, I think you have a problem like this. Differentiate something with like an e to the x down there and a cosine of x up there. You want to write this as the integral from 0 to cos x minus the integral from 0 to e to the x, and then differentiate each piece like that, using the property of integrals. Yeah, for the theorem to work in this way, the variable needs to be an upper limit. If it were a constant up there and an x down there, you need to flip them and put a negative sign in there before you differentiate. All right, it was done faster than I thought it would be. It's only about 20 minutes or so here. I think you can have 50 minutes for the mini test then. I will say before I hand it out that probably your regular midterms you're going to be more pressed for time. We're kind of warming up for harder things here. I think you should all be able to finish within 50 minutes and hopefully even 40 minutes. Hopefully maybe even 30, but you should take the time to double check your answers too.